let me introduce our keynote speaker, Professor Helmut Dersch.
Thank you, Don, and good evening. I'm glad to finally get this opportunity to meet the many people who contribute to VR imaging, and especially also those who contributed in some way to the Panorama Tools project. The invitation to speak at this conference made me spend some more time on the documentation of the basic technology, which is quite essential, but which I usually postpone for lack of time. So let's start. I hope this works now. Okay, very good. Spot the themes. So if we carry out a survey among VR photographers about the most frustrating part of their work, I bet the answer would be hiding seams. Many of us have spent hours trying to conceal transitions between stitched images, between stitched photographs, often in vain. They just remain visible. Uniform areas like skies, like in this image, are prone to this problem, usually due to color mismatch of the source images. There was a funny post to the PTViewer mailing list about someone being so obsessed by themes that he sees them outside in the real sky. I want to present some methods to handle such color problems, along with a general overview of how Panorama Tools works. By the way, this image has no seams, since it was created by remapping a single photograph made with a 180-degree fisheye lens. It's this one over there. So if you really did find seams down there, you may have spent too much time photoshopping lately. So this is the outline. Panorama Tools is a set of computer programs. Most tools are used for the creation of panoramas, and I want to give an overview of this technology first. I will start with the transformations, which have to be applied to a set of images before we can merge them together to a panoramic image. The stitcher combines these transformations into one step. To get a seamless panorama, we have to adjust both the position and color of each pixel. Viewing a panorama is the reverse operation. The most often used member of the Panorama toolset is probably PTViewer, an interactive viewer implemented as Java applet. So there are numerous clones of PTViewer under different names in use today. I will present PTViewerME, a mobile viewer which runs on cell phones and PDAs. This viewer more than doubles the prospective viewer base for your panoramas and also offers novel applications for immersive imaging. Now we start with what we are after. 360-degree panoramas in the most often used mappings: cube with the 6 faces, sphere or equirectangular, or cylinder. Discussions about the advantages and disadvantages of each format are quite popular in this community. Here I just want to mention that panoramas can be transformed from each mapping to each mapping without visible losses, of course with the exception of the limited field of vertical field of view of the cylinder format. I will use this scene and this image as example throughout my talk. We now want to create this panorama, maybe the spherical version, and start with photographic images. Maybe, oh, this is very bright. I think the gamma values are not quite adjusted here. Anyway, sorry for that. So we want to create a panorama, an image which can be fitted into this part, which is enlarged over there to the right. And we may start with a photographic image shown here to the left. This may be a suitable image. To get the same part of the scene, we have to turn the camera about 30 degrees upwards. Now, to insert this image into the panoramic image, we have to apply a series of image transformations, which are shown here. We have to correct the image, that is, remove lens distortions and other image errors. Then we have to apply a perspective transformation, like here, and then remap the final image to one of the projections mentioned previously. Correct perspective remap, this was the name of the first set of panorama tools. Those were our Photoshop plugins. There's a fourth one, Adjust, and those were published in 1998. So, the transformations are controlled by sets of parameters, which are symbolized by these icons, the correct and the perspective and remap steps shown here. I will start and discuss these in some details. I will start with the correct step. I should not move. So correct is maybe not the best way for this tool because there's nothing wrong with the original image. What we want to do is remap this image to closely resemble that of an ideal lens, either rectilinear or fisheye lens. Two main deviations from this ideal are handled. First, off-center optical axis. That means that the center of the lens does not coincide with the center of the image. Not only the following distortion corrections, but also the remap and perspective tool require exactly aligned images. Therefore, we need this first correction. Now, distortions in lenses are mainly radial type, either barrel or pincushion. In wide-angle lenses, mostly radial barrel type. They lead to convex bend shaping of straight lines in the scene. Some of these straight lines are shown here red, and they can be better seen by dimming the image. Those are the straight lines in the distorted and in the corrected image shown to the right. This error is corrected by radially shifting each pixel by an amount determined by this lens-specific correction curve. We describe this curve by a polynomial, and the coefficients of this polynomial constitute the second set of correction parameters. Also the wrong direction. Now the perspective tools, the perspective plugin or the perspective tool should transforms the images to a unified point of view and viewing direction. In this example, from 30 degrees upwards to horizontal viewing direction. Yeah, this is equivalent to tilting the image plane into the upright position here. The red line indicates the viewing direction, and it is now appropriate for this panorama. The parameters used for the perspective transformation are pan, tilt, and rotation angle, rotation around the optical axis. I have symbolized those with these three icons, and the fourth parameter is the focal length, or equivalent the field of view angle, symbolized by the zoom icon. Now the Stitcher tool combines all these three steps into a single transformation. And this is shown in this image. It's really horrible, the colors, but it's due to a gamma mismatch. Don't know what is going on here. Okay, so to the right we have again the destination image, which is the panoramic image. To the left, the photographic image, the source image. We have to start computing at the destination image here. We have an initially empty canvas for the panorama and have to fill in pixel after pixel. For each pixel position in the destination image, we have to calculate the coordinates in the suitable source image, take the color from there and insert it into the destination image. Let's start with the position calculation. For this we have to combine all the transformation mentioned in the previous slides, the correct perspective remap step, there's a fourth one, a morpher step. We not only have to combine them, but we also stack them together. That means that we do not calculate a corrected intermediate image, we do not calculate a corrected perspectively transformed intermediate image. This would be a waste of time, and it would also lead to serious image degradation because we would need to resample and quantize the image several times. Instead, there is a literal stack of math functions. Each math function takes an exact xy pair as input, does its transformation business, and then feeds an exact xy pair to the next member in the stack. This stack can grow arbitrarily large, usually about 5 to 10 math functions are stacked together, and they all preserve the full precision of the computer, which are 16 decimal digits compared to just 1 pixel diameter for a resampled image. There's also a morpher step, as I said. This morpher step is used for uncorrectable errors, or I should say uncorrectable by the 3 steps above here. For instance, unusual lens distortions or nodal point errors. All these transformations are controlled by the parameters mentioned before. The correction step requires the knowledge for the center of the lens on the distortion correction curve. The perspective tool needs pan, tilt, rotation, and so on. The remap tool needs, of course, to know what kind of mapping is required, and the morpher step needs a set of points in the image which are used to triangulate it into meshes, which are then used for the morphing step. So these parameters are usually, of course, unknown, and we have to find them out. There is a tool for that, the optimizer tool, and this looks even more horrible.
I shot that, come on.
It's Adele.
Sorry, it looked really good on my computer screen. So in the background we have the, at this stage, of course, unknown final destination panorama, part of it. In the foreground we have a window which has 2 source images, actually just the left part of the right and the right part of the left image. Highlighted are some feature points, points which show identical features in the panorama. Let's take one of these sets of points, the red one over there. And these 2 points should, of course, lead to the same point in the panoramic image up there, which we don't know yet. This requirement that the 2 points should lead to the same destination point is used by the optimizer to calculate optimized values for the parameters. This is the auto-calibration step. The destination coordinate based on the left image minus the destination coordinate based on the right image should be the same. The difference should be 0, or to be more realistic, should be minimum. And the numerical procedure uses this requirement then to calculate suitable parameters for the transformation. The same for the y coordinate. And the more parameters we need, the more parameters are unknown, the more points have to be selected for the calibration. So now that we have all the parameters together, we can calculate the position in the source image. Yeah, there remains just one problem. If we want to fetch a pixel here, there is usually none. If we enlarge this area, which is shown over there, then the calculated source position is usually off-grid. Yeah, the pixels are here, and we usually hit an off-grid position. What we then need to do is interpolate a pixel. This is shown here with a cubic interpolator. We have the 4 source pixel here shown in the horizontal plane. Vertically drawn is the blue color component of each pixel, and then a 2-dimensional surface. Interpolating all these points is calculated. And from this calculated surface, we read the blue color component for the off-grid pixel and insert this at the right position. Okay, so now we have all pixels together and can create the panoramic image. This is summarized in this image. It's again the same image from the introduction of the talk, but this time we pretend to create it by stitching 5 images, these 5 images here, one vertically up and one 30-degree up in each direction, north, east, south, west. To the right, we see the panoramic canvas and the remapped source image fitted into this canvas. Yeah, the image vertically up covers the upper half, and the other images are inserted step by step until finally the whole panoramic image is finished. Now the geometrical fit in this case is perfect, but if we look closely, this time we can clearly see seams in the image. Over here, those appear at the edges of the remapped source images. They are due to color variations in the source images. They are introduced here for demonstration purposes artificially, but they occur quite frequently in reality, and we have now to find ways to get rid of them. There are 2 main sources for color mismatch. The first one is radial light fall-off. A uniform diffuse reflecting surface, a so-called Lambert light source, appears uniform bright in each direction. A rectilinear lens captures fewer lights at large angles, therefore the image appears darker in the corners. This effect is the well-known cosine Q4 light fall-off, sometimes called natural vignetting, because it is a very fundamental limit. Vignetting due to mechanical obstacles like shades and directional sensitivity of CCD detectors add to this effect that the image appears darker in the corners. Of course, these darker areas will show up as seams, and we have to compensate them somehow. The correction tool of Panorama tools contains a radial gradient filter that can be used for this. We have now a more sophisticated tool, PTVignette, which analyzes and finds the optimum transformation. We have here a test image of a Lambert light source, which is just a wall, and it is slightly darker in the corners. This is now analyzed by looking at each point in the radial distance from the center and averaging all pixels along this green circle. What we then get is drawn here, the brightness versus the radial distance. The green curve in this graph shows the light fall off into the corner. Pixel brightness is not the same as light intensity. We have to calculate the light intensity because vignetting applies to light intensity, not to pixel brightness. Light intensity or radiance is shown here with the red curve. And the red curve is now smoothed and used as a calibration curve for this lens. If we then correct the image using this smoothed calibration curve, we get the violet curve, which is then from this corrected image. We can use this calibration curve for all images from this lens. So we have to take this measurement just once. The second source of color mismatch are exposure variations, shown here for two images. The difference is about 1 f-stop from left to right image. Now we all have learned that we should never change exposure, but sometimes it is just unavoidable. Maybe we have an automatic camera which has no manual mode, or we want to capture some details here in the shadow, or lighting changed because clouds moved in front of the sun or whatever. So these exposure variations do occur and we have to find ways to correct them. In the center of this image, now this is now really not good to see, okay. What I've tried here is create a partial panorama from the two images with different exposure. Yeah? Geometric fit is perfect, but we see, of course, this seam in the center. To the left, it's darker. To the right, it's brighter. And highlighted is here the overlapping region of the two images. This is the region which show where the pixels are shared by both images. We use this remapped overlap region to correct the images or to find a suitable color correction. Yeah, this overlap region is shown here for the left image and there for the right image. We use a statistical approach. We calculate the luminance histogram of the left image, and this is the luminance histogram of the right image. It's of course shifted to right values, to higher intensities, not totally unexpected. Using standard statistical methods, we can now calculate a transformation which transforms this into this curve. Yeah, this transformation is called brightness transfer function in image processing, and it's shown down here. It describes how each pixel value in the left image corresponds to pixel values in the right image. This is shown here for the three colors, red, green, and blue. It coincides. If you look, for instance, here, pixel value of 50 red in the left image corresponds to almost 100 in the right image. This curve can be directly used to transform one image into the other. Yeah, you can even use standard tools like Photoshop. This curve is nothing else than an arbitrary map in Photoshop language, and you can use it that way. If you apply it to this curve, you get exactly, to this image, you get exactly this one, and vice versa. This curve also reflects the nonlinear response of the camera. One f-stop factor of 2 is approximately fulfilled here at low light intensities, but at higher intensities it levels off to a factor of 1. This histogram matcher has been an experimental feature of PTStitcher for several years now, but it's undocumented because it requires quite large overlaps between the images to work reliable. The standard documented color matcher just uses a 2-parameter color brightness transformation. Okay, so now that we have a perfect panorama, we need a viewer. And the second part of my talk deals with viewer technology. Actually, viewing a panorama is technologically very similar to assembling it. So we can reuse our old diagrams here. We have just to change some of the labels. Destination is now the rectilinear corrected image here on the computer screen. Source is the panoramic image. So we have to switch these labels, and we also have to change the direction here. So we have to fill in this image, calculate the position in the source panorama, and fetch the color and insert it here. We also use a single step transformation, which is now simpler. It just consists of a perspective and a remap step. Of course, we do not need a morpher at this stage, and we also do not need a distortion correction. And we also have parameters, but fewer, only 3, pan, tilt, and zoom. The other ones are not implemented here. Also, these transformations are optimized for speed, not for accuracy. The parameters don't need to be calculated by an optimizer because the user provides them when interactively navigates the scene. There are various implementations of this PTViewer program, the most popular being the Java version. The Java version is an applet based on Java API 1.1. That means that it is compatible with computers back to Windows 95 machines. In In 2005, I have coded PTViewerME, the micro edition of PTViewer, which is based on J2ME, the Java runtime for cell phones and PDAs. The second test release from last year is also based on the gaming API of J2ME, and it is, due to this gaming API, quite fast, comparable to desktop computers. Here you see how it actually looks like. This is the panorama viewer. It displays full spherical panoramas, 360 by 180 degrees, smooth panning, zooming, and tilting. It uses the standard navigation button of the phone, left, right panning, up, down tilting, and pressing the button zooms in and out. There's also an object viewer here. Now these devices have quite limited memory, so they are certainly not suited for gigapixel panoramas. Memory size for my phone, which is a Nokia 6230i, is 2 megabyte, which means that the cubic phase images have to be scaled down to 256 by 256 pixels. Nevertheless, the images look quite crisp on the small computer display. This is a list of features. I've covered the first two already. File format is QTVR, a subset actually coded with JPEG, quite fast, about 20 frames per second on typical phones. This is the software requirement. You don't have to go through all this. It's just, I should just mention that many, if not most, phones today are pre-installed with these Java packages. Now there are many more phones today than desktop computers, though this is will probably enhance the viewer base for Panoramas considerable, but it also allows or enables new applications for VR, for instance, using VR as a tour guide. For this application, a future extension may be interesting. It is an interface to the onboard GPS in some of the phones, which is provided by a novel Java API, which came out last year. PTViewerME will in the future provide an interface to this. So I will conclude with a slide which I originally wanted to put up as first slide. It's not meant as a summary of my talk, but lists a few general remarks about the Panorama Tools project. I'm not as active in the project as I used to be, but from what I see, the project has now more users and contributors than ever. The second point here is meant as credit to the many contributors of the project, both for their suggestions of features and also suggestions of solutions for problems. There are many successful third-party projects today, open source and commercial, and next year is 10th anniversary. And I will stop here. Thank you.